Good afternoon, and welcome to my presentation. Before start, sorry for Windows again. The topic we'll present today is about vulnerability we discovered in the Windows kernel, and we will cover how we found our target and how it can be exploited. Before we get into details, let us first introduce ourselves. My name is Junoh, and I collaborated this project with JeongOh, who was awarded Most Valuable Security Researcher by Microsoft. We are both part of vulnerability research team at Theory in South Korea, and we are interested in binary reversing, Windows, macOS, or something. So the table of contents is simple. First, we will cover how we selected the target to attack the Windows kernel. We then take a look at some of the interesting bugs we found. And for about half of the presentation, we will cover exploit for the vulnerability, in particular the strategy we adopted to exploit, a reliable exploit. When I started this project, it was my actually first year researching Windows kernel security. So at first, we investigated past vulnerabilities in the Windows kernel, especially for the driver side and at CVE search site. This is a simple result, and we classified and listed vulnerabilities that occurred past 5 years. So approximately 15 driver components had at least one vulnerability. You might think that these results are enough to start the analysis, but I wanted to see quick result through manual reversing. And because these components had complex code base, so I decided to start further classification here. The first is whether the vulnerability occurred multiple times. So I wanted to find targets that were structurally weak, not just vulnerability discovered by chance. Additionally, this classification was made because there were past research showing that developers often make similar mistakes. So this condition eliminated many candidates. The second condition is whether a working exploit has been created for the component. That is because our goal was to complete a reliable exploit. So we thought this condition would increase our chances. However, because Windows bug bounty award the same amount for a vulnerability regardless of whether it can be exploited or not, so there were not that many exploits disclosed as expected. So in this condition, only 3 candidates remained. In fact, all 3 candidates, these targets were good targets. For example, CLFS continues to have vulnerabilities used in the wild, and the cloud file mini filter driver was used in local privilege escalation in Pontoon 2023. However, this is consequential story, and when we found vulnerability, we further reduced the target to 1 driver through 2 additional conditions. First, in the case of CLFS, too many experts have been paying attention since 2020 because it was widely used in the wild. Also, one of the reasons for exclusion was that there was too many vulnerabilities. And finally, the filter driver and WinSock driver remained. But as my expression hacker-friendly here suggests, I excluded it at first because I thought it was not an easy to reach target. Please refer to the good presentation below for this cloud mini filter driver. Or maybe this Synactive presented this. Yeah. Now let's take a very brief look at AFD.sys, lastly remained. It is the WinSock function driver, and is responsible for handling primary network-related functions in Windows. So you can communicate with this driver by socket handle created through WinSock, or you can directly open device AFD endpoint or device path to create and communicate with socket handler. And basically, this driver is responsible for processing network function. So it consists of very complex code, including about 70 IOCTL handlers. Although this driver has not received much attention recently, many researchers have analyzed this component in the past. Metasploit exploit exists, and it is also used as an Internet Explorer sandbox escape chain in Pontoon 2014. This means that there are a lot of good vulnerabilities that can be exploited, but it also means that shallow bug will be rare. So we analyzed whether there are code paths for these drivers that researchers might have overlooked. As a result of investigating past vulnerabilities, most of the vulnerabilities occurred in the IOCTL handling code. This is because, as mentioned earlier, there are many functions in the IOCTL of the network driver. So when analyzing IOCTL and Windows kernel driver, the function of the IRP-MJ, device control, major function entry, is analyzed. However, inside the Windows kernel, there is a fast path code that references the handlers in advance before calling them, and this is called fast IO. Fast IO handles multiple function requests to the driver by referencing the fast IO dispatch of the driver object. The code shown on the right side is part of the anti-device IO control code system core of the Windows kernel. As you can see, if the fast IO dispatch pointer exists in the driver object attached to the given handler, it is called by referring to the fast IO device control entry that exists in the table. Additionally, when calling fast IO, you can see that the IRP structure is not created, and the user's input and output are used as is. Although this is for optimization purpose, there is a risk of outdated vulnerability, such as double fetch. Now let's take a look at a vulnerability you might like. When you send message IOCTL to the socket handler, there is code in the fast IO handler that copies the C message buffer existing in user memory to kernel memory. As you can see from the pseudocode, the function AFD compute C message length first parses the user buffer and calculates C message length. Then a kernel heap buffer is created by the calculated C message length. Lastly, AFD copy C message buffer copies the C message existing in the user buffer to allocated kernel buffer. Most Windows built-in drivers like this have symbols like function name, so you can understand the approximate algorithm at first glance during the reversing. We can figure out how C message is structured by reversing the AFD compute C message length function, which calculates the total length of C message. This function retrieves the chunk size stored in the user buffer and adds it to total size according to a specific alignment. Afterward, it adds to the user buffer pointer as aligned chunk size and repeat the loop by user buffer length. This process shows that C message has some length chunk structure, and you can see that total length of corresponding chunk is stored as the result. Next, AFD copy C message buffer copies the user's C message to the kernel buffer allocated by previously calculated C message size. This function also goes through a loop that takes the chunk size value of the user buffer and copies it with memmove. Additionally, because the C message structure of user land and kernel land is slightly different, there is additional size calculation with kernel chunk size variable. The problem here exists in the process of adjusting the 8-byte alignment of kernel chunk size. The user's chunk size can be any 4-byte integer value, and in the process of alignment of kernel chunk size, the addition and 4-byte bitwise AND operations are performed, where integer overflow occurs for the aligned chunk size variable. When integer overflow occurs, the value of aligned chunk size becomes 0, so it may pass the check with size remain variable below. However, no kernel crash occurred when the POC was written. That is because there was a validation for chunk size in AFD compute C message length. So we need to cause to overflow for chunk size plus 11. But since there is a check for chunk size plus 3, we have to create large kernel heap buffer, or we will get into infinite loop in kernel. Here, we should notice that both AFD compute C message length and AFD copy C message buffer use the same user buffer to parse C message. Since this is a kernel driver and we all love multiprocessing, we can consider changing the chunk size stored in the user buffer between these two functions. If we store chunk size of a small value that passes the length validation in A, and then change it to large chunk size that causes an integer overflow in B, then we can trigger vulnerability. So how can we trigger the vulnerability in code? We just used memory value flipping. Let's assume that the user process creates a thread that repeatedly modifies the value of the user memory where chunk size is stored, and then calls the corresponding kernel code again and again. At some point, there is a 50% probability that small value, in this case 0x18, will be stored in chunk size when the length validation is performed in AFD compute C message length. After the length calculation is completed, the following code is executed, and the code on the kernel side continues to be executed, while the chunk size value of the user buffer continues to change. At some point, there is also a 50% chance that there will be a large value stored in chunk size at AFD copy C message buffer, which triggers the vulnerability when fetching value for copying. If the previously mentioned race is successful, we can successfully trigger an integer overflow for aligned chunk size variable. What happened next? We pass the check with size remain and copy a very large length to the kernel heap buffer at memmove. The kernel heap buffer to be copied here is the heap memory that we allocated in a small size in the previous race. As a bonus, there is something that always bothers us when writing real-world exploit. These are several conditions that must be passed to reach the vulnerability. As with this vulnerability, certain stage of the driver object had to be satisfied to reach the vulnerable code. Because this driver is a network driver, there will be various states and types that the endpoint can have. And since the number of states are not infinite, we simply set breakpoint where vulnerability exists and performed fuzzing for each state. As a result, we were able to confirm that the code was executed when sending a request to the bound UDP endpoint. Additionally, the code path could only be reached by 32-bit process, but it was not significant restrictions on performing local privilege escalation. However, it is unfortunate that the vulnerability cannot be triggered in 64-bit sandbox apps because we might have triggered the vulnerability with opened UDP handle. Okay, so we can cause an overflow on the kernel heap buffer. Before writing exploit, let's take a look at what we need to consider. Unlike overflows that occurs, for example, in stack, there are three things to consider when a kernel heap buffer overflow occurs. It may be obvious, but the first thing is the size of the copy destination buffer. Unlike other heap allocators, such as glibc heap allocator, where a chunk of all sizes are allocated in one place, Windows kernel heap allocator, such as LFH, only place chunks of the same size in one place. That is why we must take this condition into account. Fortunately, in the case of this vulnerability, we are relatively free from this condition because we can allocate a heap buffer of size we specify at AFD compute CMS length and use it as a copy destination buffer. The second thing to consider is whether the user can manipulate the data in the source buffer. When we exploit a heap buffer overflow, we can broadly consider two methods. The first is to manipulate the heap metadata that exists in the back chunk. And other thing is to overwrite the data of another object. In both scenarios, we need to copy certain values, so we need this condition. And fortunately, the source buffer here is the user's memory that exists in user land, so arbitrary data can be copied. The third thing to consider is the length of the data being copied. When performing heap overflow, if we cannot overflow the desired length, and then a noise may occur, such as unwanted object being manipulated. This noise is a major factor in reducing the success rate of exploit. Unfortunately, in the case of this vulnerability, we cannot specify arbitrary length of the data copied. That is because we have to cause an integer overflow, and the length of data we can copy end up being 0x FFFFFE9 to FFFFEF. Here comes the challenge. In this vulnerability, we need to copy extremely large bytes, and this huge copy makes exploitation very tricky. In Windows, unmapped memory is left after mapping a segment of certain size. So if any of this unmapped memory is encountered during the copy, kernel crash will occur. Our goal is to write reliable exploit. Then we should avoid having a high probability of kernel crash. If so, we need to consider whether there is a way to stop the copying process in Windows kernel. Let's take a look at our current situation. The source buffer being copied is the user buffer of user land. Then what happens if a page fault occurs in user land rather than kernel when copied? In fact, the Windows kernel stops copying and continues execution without causing a kernel crash. This may be a natural behavior because the user's fault should not be transferred to the kernel. If you look near the code where the vulnerability occurs, you can see that the copy function is wrapped in an exception handling statement. And when an exception occurs, it branches to the exception handling code. That is the function return. So our strategy is as follows. When passing memory to be copied from user to kernel, unmapped memory is intentionally created behind it. If the location of the source buffer where the copy begins is far from unmapped memory by the number of bytes to be copied, the kernel will terminate the copy after performing a copy of the corresponding length. In this way, we were able to copy data of arbitrary length and avoid kernel crash. Now, we can overflow arbitrary data by an arbitrary length. Then we must decide which data to overwrite through overflow. A target object to be manipulated through overflow must be selected, and several conditions are required to become a target object. First of all, In order to become a target object, the object must be able to be sprayed. The reason is that we need to place the target object right after the chunk where the vulnerability occurs. Since the kernel has severe heap noise and chunks are not allocated sequentially, heap spray technique is necessary to achieve the desired state. Here, capability of spraying means that normal user must be able to create and release the kernel object. Next, target object should provide a sufficient primitive by modifying object members. This primitive include out-of-bound read or write, arbitrary write, or something. So what primitive is needed for privilege escalation in Windows? There are two main ways to elevate privileges when writing Windows kernel exploit. The first method is to bring system privilege to the user process. To say more technically, the attacker must read the token object address of system process existing in kernel memory. For example, init process at NTOS kernel data section to the token object of current process. The second way is to bypass the permission check in kernel. This method includes changing the previous mode of current thread to kernel mode or setting the bit of SE debug privilege. The primitives required for each method are as follows. The first method requires arbitrary read and write because the object address of certain address must be read and written to specific address. For the second method, since the current thread object address is known in the current version of Windows, arbitrary decrement primitive is sufficient. Coming back, to perform a Windows kernel exploit, the target object must provide arbitrary read and write or arbitrary decrementive primitives. This is optional, but to make the target object universal for multiple exploit, the object size must be mutable. This means that the object must have a data buffer so that the user can manipulate the object data buffer size during the object allocation process. Popular objects that can do this include the named pipe object of non-paged pool and the Windows notification factory object of paged pool. However, in the case of this vulnerability, condition 3 is not necessary because the size of the chunk where overflow occurs can be arbitrarily manipulated. Therefore, we only need to consider condition 1 and 2. Since an arbitrary decrement primitive is enough, we can select an arbitrary object that contains a pointer to another object within the object as the target object. This is because the Windows kernel manages the object reference count on its own, and if the address of the object is manipulated at the time of object release, the value of arbitrary address can be decreased. So the object we chose is I/O completion context. There are actually numerous objects that satisfy condition 1 and 2 in the Windows kernel. But since it would be better if the spraying is convenient, we found an object whose reference of allocator is NT something, which is system call name. So this object can be freely created and released using NT set information file, and has another object called port as an object member. Also, other members are not very important. This is the pseudocode for allocating the I/O completion context object. After allocating an object to the non-paged pool, which is the pool where the vulnerability occurred, you can see that a port object is declared as an object member. And this is a pseudocode that releases I/O completion context. As you can see, the reference count of the member object is decreased before releasing the object. If we modify the value of this member, we can perform arbitrary decrement on an arbitrary address. Lastly, let's take a look at how the target was sprayed. Since the vulnerability is a buffer overflow, the heap funsu process is very concise. First, spray the target object using an appropriate allocation method. Next, a certain percentage of target objects are released. This is to create a hole in the sprayed target object. In this way, the buffer where the vulnerability occurs and the target object is made adjacent. Finally, we trigger the vulnerability, causing an overflow and overwriting the port member of I/O completion context. At this time, as mentioned earlier in the target object selection section, we decrease the value of the previous mode of current thread. The reason why we didn't use SD debug privilege or something is that they need to decrement a large of bits. But since Microsoft is blocking exploit primitives related to memory leaks and previous mode or something, I think this will be the last opportunity to use this. Lastly, I will conclude the presentation by looking at the exploit POC. To say more, same exploitation work for Windows 11. So actually, it just run exploit and it just pop system share. Yeah. Okay. That's the end of my presentation. Thank you for listening. You may see my exploitation after we upload blog posting, and thank you.